right, everyone. Say I love word problems. Yep. Say I love word problems. You know what I believe in. Once you show math some love, it will love you back. So today I'm gonna do some problems on uniform motion problems, some word problems. And basically it's one of your favorite topic. It's one of mine too. Ha ha ha. Rate times time equal distance. So first of all, with these type of problems, I understand the struggle. I can tell you, I have not taken my math knowledge to a master or a PhD level. So I myself have struggled over time to truly understand these problems. And so imagine trying to teach it to students who don't understand it and you haven't quite grasped it yourself. So that's just a little background on me and rate times time equal distance. So forgive me if you're still not clear on my explanations. Like I always said, if I'm your only source of knowledge in math, you will fail. You really need to seek other sources if this couldn't help. All right, moving on. So first of all, what you got to know about uniform motion problems is that there's always going to be two moving objects. So at the algebra stage, I guess if you get more advanced into physics or anything like that, maybe they'll have different other objects or movement that's occurring. But at this stage of the game, uniform motion problems in your algebra text or your introductory algebra courses or algebra course, college level math courses, it'll be two moving objects. And what I discovered is that there are two formulas, not necessarily formulas that came out into some text, but two observations that I've made that I've able to develop formulas. And one of them is that you will, from these, so each of the moving objects is going to have a rate and a time and a separate distance, right? So usually in the problems, I came up with two formulas. It's either going to be the first object, the product of the distance of the first object plus the distance of the second object that equals the total distance, right? Because RT is D, right? R times D. So this is really saying D1 plus D2, okay? Again, RT is D, D1 equals to D2. But usually they're always given your problems with pinpointing the rate and time. So when you look at your word problems, chances are if you were given the total distance that they cover together, it's the sum. So the formula is going to be R1T1 plus RT2T. Now, if you look at your problem and you don't see the total distance, but there's some key words like overtake, and alongside, right? These are just two keywords that I know this is popular. And if anything comes up in the problems that I'm about to do for you, I will let you know. But whenever you see these two keywords, not simultaneously, like overtakes, and alongside, usually the distance are equal to each other at some point. What that means is that if two objects are traveling, right? Two objects are traveling, right? And then at some point, one of them overtakes the other. So let's say object one, and object two, right? At some point, one catches up to the other. You see what happens here? Their distance are equal, right? So that's where that formula kind of come up with. Okay, so before they actually overtake, or alongside speaks for itself, right? They're alongside each other, distance is equal apart, right? But so in terms of overtaking, at some point instantaneously in time, they are going to be equal to each other before they actually overtake the other. All right, so these are the two formulas that at this stage in your text for any type of introductory algebra or college algebra course, you will you have to apply these two formulas. Let's see when and how to apply these formulas. All right. Okay, so here we have a problem. It says a car begins heading along a path at 50 miles per hour. A second car begins an hour later along the same path, traveling 70 miles per hour. For how long will the first car have traveled when the second car overtakes it? So good. I saw my keyword, so I definitely know that I'll be using Formula 2 for this question, right? Formula 2 will be used for this question. So let's see what they've given us. So, excuse me. So, you usually set up a table with three rows, three columns, right? The first column will have the rate, second column will have the time, and the third column is the distance, but not to be mistaken with just looking for a distance in your problem. The distance is really the product of the first and second column, R and T. So whatever the product is here, R times T is what you put in the third column. So we have two cars. We got car 1, remember I always say it's going to be two moving objects, and car 2. And let's see what they've given us. They've given us the rate for the first car, right? So the rate was 50 miles per hour, if your professor is concerned about units. And the second car is given a rate at 70 miles per hour, right? 70 miles per hour. So let's see what they said in terms of time. It said the second car begins an hour later. Now, an hour later, but we don't know what time the first car started. So that's my unknown. That's my unknown that I represent with a variable X, Y, Z, doesn't matter. So I don't know what time the first car started, but it's telling me that the second car started an hour later after the first car. So you represent later with that -1. Great. So now remember I told you that the third column is the product between the first two columns, right? So this is 50 times X, right? And this is actually 70 times X minus 1, right? So now, so here I have my R1 T1 and here I have my R2 T2. So like I said, because of the keyword overtake, I'm going to set them equal to each other, and then I explain why it's equal to each other. So here we go. So here we have 50X, right, equals to, and what I'm going to do, I'm going to do the distributive property here with this factor times this group of terms. So that's 70X minus 70. And then I'm going to solve for X because the question is asking, right, how long after the first car have traveled will the second car overtake it? So it's actually looking for the rate. So it's looking for the time of the first car, right? Because it says for how long will the first car have traveled. So it's actually just looking for the time for the first car, which is X. So all we have to do here is solve for X. So I am going to make sure that all my variables are on one side of the equation, and I have a choice. I can bring put all the X terms on the X side, on the left side, or I can put the X terms on the right side and put the constant term on the left side and vice versa. But I'm just, I like working from left to right. I don't know if it's because I'm a lefty, but here we go. So I'm going to subtract 70X. I'm going to transpose the 70X from both sides. So now here I have the difference between positive 50 and negative 70 as negative 20X. Equal to negative 70. Breathe easy. We know we can't have a negative time, but if we have two factors, so I'm going to divide the factor 20 to solve for X of a negative factor, we know we have a positive. So if we look at this is an easy cancellation. They have a common factor of 10, so I'm left with 7 halves. And if I was to break that to find it hours, is 3.5 hours. So the first car, that's what they're looking for. So the first car was traveling 3.5 hours before the second car could overtake it. Now, another way they could have asked the second question is how long it took for the second car to overtake the first car. And that way you'll just have to subtract 3.5 minus 1. And then you would have gotten your answer. Okay, let's try another problem. Good. So here we have two runners begin jogging in opposite direction from the same point at the same time. One runner jogs 1 mile faster than the other. In half an hour, the joggers are 6 miles apart. Then so if in half an hour the joggers are 6 miles apart, then how fast was each jogger? All right, so we'll set up our table. So we have our 3 columns with the rate, the time, and the distance. And we have 2 moving objects. In this case, it's 2 joggers. So let's see what they give us. 2 runners, right? So here we go. I call them joggers because they were jogging. So is there such a thing as a jogger? Maybe. Anyway, so they're going in opposite direction. They started at the same point at the same time. Same time. All right. So they both share the same time. One runner jogs 1 mile faster than the other. So we don't know how much, and I guess it doesn't matter. We don't know how much one of the runners jogs. So we'll just assume that, and that's the rate, right? Miles per hour. And then the other one is, so this is the unknown. We don't know how much, but we know the other one is a mile faster. So at first, the first problem we were doing was later, and we represent it with a minus. Now we're going faster, we represent that with a plus. Now the key is, as I said, in half an hour, remember they started at the same time. Okay, so in half an hour, right, the joggers are 6 miles apart. So in half an hour, they're giving us the total distance between the two of them. Okay, so here we go. We have a total distance. So therefore, it looks like we'll be using Formula 1, which equals total distance. So we have a total distance. All right. So here we go. Remember, our third column is this. You can't put 6 here. You can't put the total distance 6 here because this is not the total distance. Total distance belongs to both joggers. Okay, so you still have to set up your third column as the product RT, because we don't know what was the rate and the distance of each as yet. Okay, so our third column, don't forget, is the product of the first and the second RT. So this is X times a half. Remember, math is commutative. It doesn't matter if I have it in the reverse. And this is X plus 1. Multiplication is commutative, not math is commutative. All right, so now I'm going to be using my first formula because I've been given the total distance between the two. So here we go. This is a half X plus a half X plus a half. I distributed the half to the terms over here, and that's equal to 6. So now I'm going to solve for X and try to answer the question. So here we go. A half X and a half X, we get a whole X. So that's 1X. We don't need to write 1X. That's redundant. So that's 1. Oh, this is a half plus a half equals 6. So I'm going to solve for X. So this is X equals to 6 minus a half, right? And if I could use fraction or I could use 0.5. But I like working with fractions since I'm not using a calculator at this point in the game. So this is actually 12 over 2 minus 1 over 2, which is 11 over 2, which is equal 5.5 or 5.5, right? So we see the question is how fast is each runner each jogging. So that means we have to find the rate for both. So one is jogging at 5.5 miles per hour, which was X, and the other one was X plus 1, which is 5.5 plus 1, which is 6. So your solutions are 5.5 and 6. All right, I'll do another video with some more problems. If not, this will be really long.